We're going to make the transition today between simple harmonic motion and mechanical waves. A mechanical wave is something that carries energy from one place to another. The example that I gave you a few minutes ago during the demonstration would be the swimming pool. When I'm lying on the air mattress in the swimming pool just getting some sun, and somebody jumps off the diving board on the other side of the swimming pool into the water, and that causes me a couple seconds later to start bobbing up and down, I got kinetic energy from somewhere. Not from nothing, but I got it from something. The place that I got it from was the person jumping into the water. He or she had kinetic energy that ended up getting transferred to me via the water wave. We also talked about the earthquake in the Indian Ocean 10 or 11 years ago that caused this massive tsunami that killed 100,000 people. There was a massive earthquake which supplies a lot of energy. Well, that energy ends up getting transferred to the shore via a water wave, and hence the tsunami that ended up wiping out a whole lot of people. Do you know that 30 hours after that tsunami, 10 years ago, 11 years ago, whatever it was, 30 hours after that, the swells, the waves off the coast of Nova Scotia were measured to be upwards of 1 meter high, and they attributed that to this earthquake that took place across the world, on the other side of the world, in the Indian Ocean. Waves carry energy. That's what they do. All the way from the Indian Ocean to the North Atlantic Ocean off the coast of Nova Scotia. That's the whole point of waves. They carry energy from one place to another. Now, how do they do that? It's not just magic. They do that via the simple harmonic motion of individual particles within the wave. Individual particles vibrate back and forth. Back and forth. Maybe one way, perpendicular, or maybe parallel. That doesn't matter. They vibrate back and forth. That's simple harmonic motion, motion that repeats itself, motion in which the restoring force is proportional to the displacement. That's what carries the energy from one place to another. And when we put all those individual particles undergoing simple harmonic motion together, we call it a wave. Now, we said in our demonstration there's two kinds of mechanical waves. One's called the transverse wave, and the other's called the longitudinal wave. The transverse wave is the wave that is traveling on one axis, let's say the x-axis here, and has its particles vibrating on the other axis, perpendicular to the direction of motion of the wave itself. So the energy is transferring to some guy, hey, let's say it's Liam, standing over here on the right. The energy is being transferred to Liam on the right-hand side. The simple harmonic motion of the particles is up and down, up and down, up and down, perpendicular to the left-right motion of the wave itself, the transfer of energy. Now we're going to label some things on this wave. Firstly, a crest. The crest is the bump on a wave, or we could say it's the top of a wave, or the peak of a wave. When I was your age, taking my driver's license in Nova Scotia, I remember seeing in the driver's manual, just like there is in the Alberta driver's manual, a page with a whole bunch of signs that you had to memorize. This is a school zone. This is a whatever. There was one sign that we see out there that we don't see really out here. It just isn't used out here. It would say blind crest. I'm pretty sure it's not in the manual out here. A blind crest is that sign that you would see when you're going up a hill, but you couldn't see over the top. And they put that sign there because sometimes maybe there's another road coming out perpendicular to you at the top, or maybe somebody's driveway, and somebody might be pulling you out onto the road, and you won't be able to see them until after you cross the crest of the hill, the top of the hill. So a crest of a hill is the top of a hill, the peak of a hill. And a blind crest is this hill that you can't see over the top. Okay? The crest of a wave is the peak of that wave, or the top of that wave, that if you're going up it on one side, you couldn't see over it on the other side. So the crest is the peak of a wave, versus a trough, which is the valley of a wave, or you could say the dip in a wave, or the bottom of a wave. Kind of think of it like a feeding trough in a barn. You get this half pipe, that's a feeding trough. It's got all the food in there for the animals, and they just put their head in there and dig down into the valley of the feeding trough to get their food. This would be a trough, by the way, as well, and this would be a crest. Now, you don't just have one crest and one trough. You got everywhere where there's a bump or everywhere where there's a peak, you call it a crest. Everywhere where there's a valley, you call it a trough. The wavelength is the distance over which the wave repeats itself. So in other words, it's essentially the length of the wave. The distance over which the wave repeats itself. If we start at the top of a crest, the distance over which the wave repeats itself would be from that crest to the other crest. The symbol for wavelength is a Greek letter called lambda, L-A-M-B-D-A, and it basically looks like an upside down Y. Now you can label lambda or the wavelength in other places as well. You can label it here. The wave repeats itself over that distance. Or we could label it here. The wave repeats itself over that distance. Anywhere on this wave that measures the distance over which the wave repeats itself would be called the wavelength, given by the symbol lambda, and usually measured in meters. Finally, the amplitude of a wave is the height of a wave. Symbol for amplitude is A, but we won't worry about units for that because we're not going to do any calculations involving amplitude. The amplitude is the height of the wave, though, given by the symbol A, and it's related to, not directly related to, but it's related to the energy of the wave. How many people have ever been in a wave pool? Most of you have been in a wave pool. You know that when that wave producer starts, the waves are pretty small. You feel some energy, right? The wave gets bigger, and the energy of that wave, like you can feel it, goes dramatically up. It makes it a lot more difficult to just stand there and have the wave go up against you without knocking you over. The amplitude, as the size of the wave, as the height of the wave gets bigger, the energy gets bigger exponentially. So if you double the height of the wave, you're not doubling the energy in the wave, you're quadrupling the energy of the wave. If you increase the height of the wave by a factor of 3, then you're increasing the energy of the wave by a factor of 9. So the energy goes up exponentially with the amplitude. They're related to each other, the energy and the amplitude, but not directly related to each other. The other kind of wave is what we call longitudinal wave. This isn't the best diagram for a longitudinal wave, but it's the best I could do on Microsoft Word. The longitudinal wave is that second wave that I showed you in the demonstration where we have that series of high pressure areas within the medium, the spring in the case of the demonstration, and then low pressure areas, and then high pressure, and then low pressure, and so on and so on and so on. We call those high pressure areas compressions, high pressure or high density. In the areas that surround the high pressure or compression areas, we call rarefactions, R-A-R-E factions, low density areas. They would be roughly equivalent to the crests and troughs of a transverse wave. In fact, if you plotted, you don't need to write this down, what I'm about to show you here, but if you plotted a graph of intensity versus distance. Over here, it was y-axis versus distance. But if you plotted intensity versus distance, you would find that you would get areas of high intensity, sorry, not intensity, but density, I should say. It's okay, you don't need to write this down. low density right here where the particles are far apart, and high density right here where the particles are close together, and low density, and so on and so on and so on. So if you plotted density versus distance instead of distance versus distance, you would get a graph that looks the same. Now, it's more difficult to visualize the wavelength and amplitude and so on of a longitudinal wave. We'll try a bit here. The wavelength can be measured from here to here, because that's the distance over which a wave repeats itself. Or it could be measured from here to here, because that's the distance over which the wave repeats itself. Or any other place to a place down the road where the wave repeats itself. Remember the fundamental difference, though, between these longitudinal waves and the transverse waves? Transverse, the wave is going to the right, the particles are vibrating up and down. In the longitudinal, the wave is going to the right, and the particles are vibrating to the right and left. So perpendicular to the motion of the wave and parallel to the motion of the wave. The speed of these waves, transverse or longitudinal, is constant. How fast these waves travel doesn't change unless they go into a new medium, or shallower or deeper water, or unless something in the material changes. Light waves go from air to water, the speed changes. Water waves go from deep to shallow, the speed changes. But as long as the conditions don't change, then the speed doesn't change. Because the speed of a wave is constant, we can express it by this equation, v is equal to delta d over delta t. Right? It's the uniform motion equation. It's the group A equation that we learned on day 1 of physics 20. V is equal to distance over time. But I want to do a substitution here. The distance over which the wave repeats itself is called what? No, not the displacement. The distance over which the wave repeats itself is called the x thing. What did you say? The wavelength. Good. It's the wavelength. So we're going to say the distance over which the wave repeats itself is called the wavelength. The time over which the wave repeats itself is called the... You know this. It's the time over which... Yeah, it's the period, the time for one complete cycle, right? It's the period. Now, what I'm going to do here, not that I have to do this, but I'm going to do this substitution because of the way that it appears on my data sheet. I'm going to replace t with 1 over f. And then my equation becomes v is equal to lambda over 1 over f, or we could say v is equal to f times lambda. We call this the universal wave equation. And it describes the speed of a wave, the constant speed of a wave, not using its displaced distance and time, but rather using its frequency and wavelength. Now remember, this one is still valid because a wave travels at a constant speed. It's just that the last one, the new one that we've learned, is unique to wave motion. Whereas the first one is valid anytime we have constant motion. Questions on page 409 says, to generate waves in a stretched spring, you oscillate your hand back and forth. What does oscillate mean again? Cal, we're not done there. But what does oscillate mean? Back and forth, simple harmonic motion, right? You move your hand back and forth, repetitive motion, simple harmonic motion, at a frequency of 2 hertz. Speed of the wave is this. What's the wavelength? It's a very straightforward question. Remember that when we're analyzing wave motion, we're allowed to say v equals delta d over delta t, and we're allowed to try v is equal to f times lambda. Looks like we're going to use the second one in this case. Just remember the first one is still there. We're allowed to try it. V is equal to f times lambda. Rearrange to solve for lambda. V over f. That gives me 2.70, and the units for that would be meters. Got a handful of questions for you to work on page 409 right now. Same thing, remember, right? These are all going to involve uniform motion of waves. So you can use v equals delta d over delta t, and you can use v is equal to f times lambda. And you can also use t is equal to 1 over f in there if you need to as well. Give those a try.